All right, good morning, Saintsmen. We're going to be working on the properties of radicals and discuss what a radical expression is. A radical expression is any of these expressions that just plainly contains a radical in it, all right? So some things that we've discussed before. The default here, this right here, this thing is actually referred to as the radicand, okay? The way that this thing functions is it's used to perform a particular operation. When we have a number that's inside of it, for example, we may have the number 7. 7 does not have a perfect square within it. It's not a perfect square. In other words, we talked about square numbers before, right? 1 squared, 2 squared, 3 squared, etc., which is going to be like 1, 4, 9. And any of these numbers is what we're going to look for. So let's write out the first 10 of them, okay? Because this is going to help us back our way into some solutions here. Okay, so 16, 20, 25, 36, 49, 64, and 81. The default is that this right here, this little shelf, the default is that this is a 2 when nothing is written here. So this is a square root, okay? But a radicand could also potentially have what's called a cube root, which means that it's saying that something where we're taking the, if we were taking it to the third power, right, the inverse operation would be the cube root. In fact, really anything here can have an x root. So that's what we could do here, is that we could take some sort of a root there, 10th root, 5th root, and what have you. We're going to actually stick to today just squares and square roots and cube roots. So what we're going to be worried about is here for this radicand. This guy is a square root, and here this guy is a cube root when we have a 3 written on that little shelf on the radicand. Okay, so let's simplify a few of these. Let's take, for example, rad 147. Okay, and it's said rad 147. I'm not trying to sound cool. I'm a math teacher. It's difficult for me to be cool, so I'm not saying rad because it's some sort of a hip word. It's referring to the radical. Some people say root, but I think root can be a little bit ambiguous because it may be referring to, it's not just by default square root, and that's the way people use it. So I prefer not to do that because it can be a cube root. It can be an nth or x root. So this is what we will describe as rad 147. Now, 147 has a factor in it that's a cube, has a square factor. So, and this is how I know. We have to perform a divisibility test here, and I told you guys about this one. If we go 1 plus 4 plus 7, right, that's the divisibility test for 3. It's also the divisibility test for 9. Things are divisible by 9, they are divisible by 3. But we're going to try to use that in some of the basic divisibility tests. For example, for 2, it's going to be that it's just even. This one, you add them up and add the digits up, and if they're divisible by 3. 5 ends in a 5 or a 0, right? 6 if it's divisible by 2 and 3, all right? That's going to get us through quite a bit. 1 plus 4 plus 7 is 12, which is divisible by 3. So we wind up taking 3, and 3 goes into 147 49 times. And as we know, that is square. Rad 3 isn't, but rad 49 is. So the way I usually do it is I separate these things out. The square number we can take a square root of, and that guy's going to come out of the radicand. But whatever is not square, 3, is stuck inside. So this is our simplified radical expression, okay? And I always want radical expressions to be simplified. Next one. We're going to start maybe moving a little bit. We could actually do another one like 108. Again, 108. Well, 1 plus 0 plus 8 is 9. Well, that actually means this guy's divisible by 9. That's great. So we do our radical here. It's 9, and how many times does it go in? But it goes in 12 times, right? 9 times 11 is 99. And now watch this. What's 9 times 12? Well, this is the square root of 9 times the square root of 12, which means the 3, which is the square root of 9, can come out, but 12 is stuck inside. However, this is not simplified. The reason why is because we didn't take the biggest square number inside of 108. Watch. 12 can be separated as the factors of 4 times 3. The reason we want to do that is because 4 is a square number, meaning that we can take that guy out of the radical. When he comes out, the 2 is being multiplied by whatever's on the outside, and the 3 is still stuck inside, leaving us with 6 rad 3 as our final answer. Wait, we could have done that a little bit differently. Well, it turns out there was an even bigger square number inside of rad 108. What we could have done all along is we could have said 36 times 3. Okay, multiply 36 times 3, it's 108. Most people don't know the 36 times tables, right? If we had actually just stopped back at the beginning and said, well, 1 plus 0 plus 8 is 9, which is divisible by 3, we would have actually yielded this in the first place. This is one of those things was kind of an accident, but it's okay. We're going to get the answer a little bit quicker here, right? The square root of 36 is being 6. It comes out of the radicand, right? It's going to come out. And the square root of 3 is just 3, so it's 6 rad 3. It's the same answer, okay? But it just shows that you can't leave this guy just as is. It's like when we're simplifying fractions. Here's an example. If I were simplifying the fraction 10 over 20, I divided both things by 5. Excuse me, I divided both things by 2, or by 5, right? But I divide them both by 2, and I'm going to get 5 over 10. Which can still be divisible by 5 to give me 1 over 2, right? I couldn't leave it as 5/10. I'd have to continue simplifying until I got the simplest form of that fraction. It works the same way here with radicals. I didn't finish the job when I was here, or excuse me, when I was here. I still had to get all the way down here because 12 wasn't simplified inside of that radical, okay? We can do the same thing with exponents. So we can have something like 25x to the 5th power. Okay? You'll hear me say many times with things mathematically, first deal with the numbers, then deal with the letters. Okay? That applies here. First of all, let's take the square root of 25, okay? First deal with the numbers. The square root of 25 is 5. Next, let's deal with the numbers. The square root of x to the 5th. Well, you do it like this. The square root of x to the 5th means that we have 5 divided by 2, okay? What's 5 divided by 2? Well, it's 2. Remainder 1, okay? In other words, what we did here is really 25 times x to the 4th times x. X to the 4th times x is really x to the 5th. The square root, whenever we do that, we're just going to divide that by 2, right? As we did previously when dealing with radicals. So that guy gets divided by 2 effectively, which is how we get this, all right? Here's our answer. Let's do another one of these just as an example, okay? Let's take rad 75 y to the 9th, okay? So let's have our radicand. 75 is 3 times 25, okay? Y to the 9th is really y to the 8th times y. So then let's keep going. You have a radicand. Let's first deal with the numbers. 5 comes out, 3 stuck inside. Take this guy. Square root is going to be y to the 4th with the y stuck inside. Some of you may be seeing a shortcut here, say, oh, all you have to do is divide by that by 2, and then you're going to take, right, it goes in 4 times remainder 1, and then you're going to have that as your remainder. And that's a great way to actually think about that problem. Okay. Let's do some more. We're going to take the square root of 11 over 36. Okay. Well, the entire thing is in the square root. Okay, you have to be careful when you write these. It means this guy's underneath as well. What this means is that we have the square root of 11 over the square root of 36, which is going to be pretty straightforward because the square root of 11 is just rad 11. It's not simplified, right? There are no square numbers inside of 11. Even think about what number is going to be half, right? Half of that's, 5.5. But in terms of having factors, and the only other factor that's less than that is going to be 4. 4 doesn't go into 11, so we're set. 36 square root is just going to be 6. So this is your answer right here, rad 11 over 6. Okay? Same thing with variables, right? Let's take the square root of 121 over n squared. Okay. Well, this is going to be just kind of simplifying the process. Square root of 121 is 11, comes out, and square root of n squared is just n. That is fine just as it is. Let's do this with some cube roots. Okay. Let's take the cube root of 135. Okay. Well, we have to think about factors of 135 that are cubic numbers. Okay. Well, 135 winds up being, it's divisible by 5, which means we have 5 times 27, okay? 27 right here, this guy's cubic. 3 to the third power, right, is 27. So what we're going to have here is this guy's going to be, 3 is going to come out, okay? Still the cube root, and we can't take a cube root of 5. So 3 times the cube root of 5 is going to be your answer. A fun one. Let's do another. Let's do one with a variable now. The cube root of 8x to the 4th power. Okay. First deal with the numbers, then deal with the letters. Okay. So here's our cube root. Can we take a cube root of 8? And the answer is yes. So it turns out 2 to the 3rd power is 8. So the cube root of 8 is 2. Can we take a cube root of this? Well, how many times does 3 go into 4? It goes in 1 time, x to the 1st, with a remainder of 1, x to the 1st inside. Here is your simplified answer. Okay. Cube root of n squared over negative 1,000. Can we take a cube root, right? Because what we have here is the cube root of n squared over the cube root of negative 1,000, okay? We can't take a cube root of n squared, right? 3 does not go into 2, so this guy's stuck. Now, as it turns out, negative 10 raised to the 3rd power, right, means negative 10, as long as we have it like this, right? Negative 10 times negative 10 times negative 10, right? So that means that this guy will be negative 10 times negative 10 times negative 10 will be negative 1,000. So there's our answer right there. It's negative 10 is what's going to go in the denominator. Okay, and we're done. Just ways that we can kind of think our way through this. Okay. Let's talk about rationalizing the denominator. This is actually one of my favorite algebraic skills. I think this one's kind of a fun one, okay? And it works like this. We get stuck sometimes with radicals in a denominator. And here's how we're going to get rid of them, okay? Let's say that we have the square root of 7 over the square root of 2x. Okay, by rule, one of the rules we have here mathematically is in your simplified form, no radicals are allowed in the denominator. Okay, so What we're going to do here to get rid of that is that we know that if we square a square root, it effectively undoes it. Like here's a just a little thought experiment for you. 3 times 2 is 6. 6 divided by 2 is 3. Okay? So in other words, if we take times 2 and then divide by 2, we have the same result from start to finish. 3 plus 2 is 5. And 5 minus 2 is 3, right? We start with 3, we end with 3, but plus 2 minus 2 yielded the same exact answer from start to finish. The same thing exists with squares and square roots, okay? If I take 3 squared, which is 9, and then the square root of 9, which is 3, right? We can actually do that backwards, all right? Means that if we square the square root, if we take the square root of 3 times the square root of 3, okay, if we recall, that's actually just going to give us 3. It's like times 2 divide by 2, or divide by 2 times 2, right? 3 divided by 2 is 1.5, and if we multiply back by 2, it's going to give us 3, right? 3 minus 2 is 1. Add back the 2, it's still going to be 3. So the same thing works here. We square the square root. Effectively, rad 3 squared is 3. Okay? So just a little bit of a sidebar. What we want to do here is get rid of that radical in the denominator. So here's what we're going to do. We are going to multiply the whole thing by its multiplicative identity, which is 1. Here's what my 1 is going to look like. Right? Isn't rad 2x over rad 2x equal to 1? 5 over 5 is equal to 1. 1,000 over 1,000 is equal to 1. Or we could just say Sebastian over Sebastian is 1, right? Anything divided by itself is going to be equal to 1. So this right here is our 1. We have made no material change to this number. But watch, it just happens to change the way that we express this. Let's take the top. Rad 7 times rad 2x is rad 14x. And then we have rad 2x times rad 2x. And as we saw before, you multiply a radical times itself, the radical gets undone. Here is our simplified answer. This is how we can express this. It means the same thing as this, rad 7 over rad 2x. It's the same exact thing. It's just expressed differently, and it's expressed properly in simplified form without a radical in the denominator. Let's do some more practice. Let's take rad 10 over rad 3. Well, rad 10 over rad 3, we have to multiply times 1. Rad 10 times rad 3 is 30. Rad 30. Rad 3 times rad 3 is 3. We're done. Rad 30 cannot be simplified. There are no square numbers inside of it. So we're all set. Okay. We could do, this is a popular one. 1 over rad 3. 1 divided by rad 3. Well, let's work on this guy. We're going to multiply by rad 3 over rad 3. 1 times rad 3 is rad 3. Rad 3 times rad 3 is 3. That's my answer. Okay. How about rad 2y squared over 3? Well, this guy's the same as rad 2y squared over rad 3, which we're going to multiply by rad 3 over rad 3. Okay. Let's see what happens. Well, this guy's going to have the square root of 6y squared. More on this one in a moment. And then rad 3 times rad 3 is 3. But we're not done yet, because look at this. 6 is a square number. That guy can't come out of the radicand. But y squared, we know the square root of y squared, right? The square root of y squared is what? Then you have to deal with the letters, right? First deal with the numbers, then the letters. Square root of y squared is y. 6 is stuck inside. 3 was always on the bottom, and that is our answer. Y rad 6 over 3. Okay. We can do the same thing with cube roots for the record. 5 over the cube root of 4. Well, the way we get rid of that is we're going to multiply, right, by something that's going to make it where we can get rid of that cube root of 4, okay? Where can we take a cube root? We need to multiply by 1. Doing that with a square, a cube root is a little bit different. Here's what I'm going to do, okay? I know, this is tricky. Where did you get that from, Granados? And it has to do with this. Let's take a look at this guy. We have 4, okay, is going to be the result. But we have something to the third power, and right now it's equal to 4. That doesn't help us. We want something to the third power that's going to be a cube number. So we're going to multiply here by 2, and then we're going to get 8. We can take a cube root of 8. Here, x is going to be equal to 2, right? 2 to the third power is 8. Okay? So what I needed to do to 4 was multiply by 2, okay? So let's watch what happens here. 5 times the cube root of 2 is 5 cube root of 2. Nothing changes there. But the cube root of 4 times the cube root of 2 is now the cube root of 8. And we can simplify that. 5 times the cube root of 2 over the cube root of 8, which is just 2, is that. And that's your answer. Okay? Kind of a tricky one. Last but not least here, we're going to start rationalizing denominators with a conjugate, okay? And here's the conjugate. 4 plus 2 minus rad 5, okay? Let's go back. Let's take the difference of two squares, right? Here's why we care. X plus 7 times x minus 7. This was a difference of two squares. If you guys recall, the result of this guy is x squared minus 49, all right? This was the instance where we had a binomial, right? We have two terms, and when we multiply these two terms, right? Typically, when you multiply two binomials, you wind up with a trinomial, except for in this instance, where the b term is negated in the FOIL pattern, because these two terms cancel each other out, the outer and the inner. Plus 7x, minus 7x, right? Those guys are going to go away, but the x squared portion and the negative 49 are going to stay, okay? So we're going to multiply by what's called the conjugate. Okay? We need the conjugate of this because we have a radical in the denominator. So all we do is we're going to rewrite this guy, but we're going to change the second term and change the sign. So rather than 2 minus rad 5, we're going to do 2 plus rad 5. It's going to help us get back to this difference of two squares. And again, so we're multiplying by 1, we're going to do the exact same thing in the numerator. Okay? Watch the result. 4 times 2 plus rad 5. And then we're going to FOIL here. 2 times 2 is 4. I'm going to have plus 2 rad 5 minus 2 rad 5, okay, which is going to cancel. And then negative rad 5 times rad 5, which is just 5. You guys see what we accomplished there? That's great. So now we have 8, because we're going to distribute on the top, plus 4 rad 5 all over negative 1, okay? It's usually enough to say this is where we're going to go, but we're going to divide both of those terms by negative 1. It's going to be negative 8 minus 4 rad 5, and this is your final answer. And sometimes we'll wind up with that negative 1. Sometimes it's just going to be another integer. But the key is that it got us an integer in that denominator, okay? Let's do some more of these because I love these problems. These guys are great. Use another one. 3 over rad 3 plus 1. So let's multiply by our conjugate. What's our conjugate going to be? Well, it's going to be rad 3 minus 1, right? Just take the same exact thing and switch the sign of the second term for the denominator. Rad 3 minus 1, okay? So now here, I have 3 times the quantity, rad 3 minus 1. I'm going to have to distribute that 3 in a moment. And then I'm going to take rad 3 times rad 3, which is 3. The outer inner are going to cancel. If you guys don't believe me, I mean, you can just keep doing it every time. Minus rad 3 plus rad 3. I think that's a waste of time. It's just going to cancel. And then I have 1 times negative 1, which is negative 1. 3, rad 3, right, because I'm distributing, minus 3 over 2, which is 3 minus 1. That's your answer. Can't change it. Nothing can be simplified there. One more of these. 12 over rad 2 plus rad 7. Let's multiply by our conjugate, okay? It's going to be rad 2 minus rad 7. And then, of course, I got to mimic the same thing in the numerator. Okay, so I have 12 times the quantity rad 2 minus rad 7. Rad 2 times rad 2 is 2. Outer inner is going to cancel, right? Plus rad 14 minus rad 14. And then positive rad 7 times negative rad 7 is negative 7. Okay? Distribute. I have 12 rad 2 minus 12 rad 7 over negative 5. That's my answer. That's all I got for you for today. If you have questions for me, you can just get a hold of me on email or through Canvas. Thanks.